All right. Hey, everybody. Hope you had a great weekend. Let's see. So we're going to keep going with our discussion about waves. And in particular, today, we're going to start focusing in on chapter 16 and the idea of traveling waves. This is going to be a topic that is going to come back again substantially when you get into Physics 314, because this is the sort of language that we use to describe electromagnetic waves and radiation. And the game plan is to spend today and tomorrow on chapter 16 to introduce this idea of traveling waves. And then with the time we have left on Wednesday, to introduce a few specific sections from chapter 17 that focus on what happens when traveling waves interact with one another at some point in space, this idea of superposition. So that's the game plan. Thank you guys very much for getting your written homeworks in. I will be grading those this week and hopefully get those posted by Friday. So everybody can see how their grade stands. For the fourth written homework, I had made this announcement that the fourth homework will be open and made available. That will cover these ideas about rotation, waves, and thermodynamics that we've seen at the end of the semester here. But alternatively, if you would prefer to resubmit a previous written homework, I'm offering that as an option for your fourth assignment, that you can do a resubmission of a previous score, and then your three highest written homeworks will count towards your final written homework grade. And I'll send an announcement with the details about how we're going to handle written homework number 4 later this week. Okay, so let me go ahead and share my slides. Okay, so we are covering 2 chapters this week, chapters 16 and 17. We are covering select sections from those chapters, and in the announcement that went out late last week, you can see in that announcement the specific chapters that we'll be focusing on. So you do have 2 online homework assignments due this coming Sunday from 16 and 17. But they're smaller assignments that just focus on those select sections. So I think the total is that those will be about the same number of problems that you would see in one standard homework set. So I'm seeing a question from Ricardo about when will extra credit be added to your scores online? So that's been happening the entire semester. So you should see in the grade book a column for extra credit that has been recorded, and that's going into your your online homework score that is posted to the gradebook currently. So that is already accounted for in the current running grade totals. Okay, and for next week, we are going to be, okay, so a follow-up question, it's asking, does it automatically do that? So it doesn't. So it's possible that the extra credit is maybe a week behind what you're expecting or something like this. I do have to go in and do some manual transaction on that. So if you're asking if it's up to date, I would have to double check it and see if it's current, or if there's a new update on that, and I can take care of that this week. Okay. Chapter 14 and 18. Chapter 14 introduces the idea of fluids. So next week, we're going to spend like one day on chapter 14, picking out some highlights from that. and then spending our final week introducing the idea of thermodynamics in chapter 18. And again, there will be a homework assignment, our homework assignments due that following Sunday from both of those chapters, but each of them will be a smaller than typical assignment to cover the select material that we're interested in. And I will convey the specific sections that we're focusing on in the announcement this week. I also wanted to point out that this week in physics, we are hosting Professor Carlo Rovelli. He's a physicist of some renown that is being honored as our Watkins Fellow this year. This is an honorarium that goes around to a representative that does work in liberal arts and sciences. And this year they're representing physics. These are world-class physicists that we bring in to give a public lecture as well as a physics seminar, and they also meet with students and faculty to talk about their work. He is giving a public lecture tomorrow at noon on Zoom. And the title of his talk is Making Sense of Quantum. Do Things Exist by Themselves? You can see this overlaps with our course, with our schedule with when we normally have class. I would personally like to go to this, and I would like to have you guys have the opportunity to go. So tomorrow we'll probably cut out about 10 or 15 minutes early. I know that puts it at 5 minutes late, but they usually get going about 5 minutes late, waiting for people to connect, so that people can connect to that if they would like. And I will share the connection details around in an announcement if people are interested in attending that. So we'll have a bit of a short class tomorrow. Okay, I think that's all the announcements. Are there any other questions before we get rolling on materials? Okay. If not, I'm going to go ahead and switch over to share my browser because I want to start with a video and a bit of a simulation demo here. Okay, I'm going to go ahead and get my screen sharing. Okay, so to kick things off for this chapter, we're going to be talking about traveling waves. And to get going, I just want to show this demo of a traveling wave being set up on a string, and then we can talk more about this as we go along.
To study, so I've been by making an initial pulse like this. So here's a couple that you may recall seeing. And here, I'll do another one. So here it is, and we let it go. And we get our pulse going back and forth.
Okay, so you just saw in that example that this gentleman displaced the string, right? He has a taut string that's held out between these two posts. He changed, right? So there's some equilibrium position. It has this natural shape that it likes to fall on, and everything's at rest. And then what he did is he perturbed the material from that equilibrium position, and he let it go. And you saw that kind of triangular shaped pulse that he created move out, right? Travel down through the medium and create this moving wave pulse. So this is the general idea of a traveling wave. Those things we just talked about are the ingredients that you need for any kind of traveling wave. You need to have some medium, some collection of particles that interact, so that make up a rope or make up some air volume or some solid. And then you need to have something cause a physical disturbance away from their equilibrium position. And if those, right, if that object has that the particles near one another like to hold on to one another and exhibit forces one another, what happens is that displacement or disturbance in the equilibrium position then travels through the material in what we call a traveling wave. So you can produce a traveling wave as a displacement of the string's position here, but you could also imagine having a traveling wave in air, right? As I'm talking to you, this is a traveling wave that's coming out from my mouth to the microphone. And what's changing is there's a fixed air pressure, and I'm making local variations in the air pressure, and those air pressure variations travel through the air like this pulse down a string. You could also imagine having a spring system, and I could compress the spring in one position and let it go, and I could watch that pulse travel back and forth down the string. Let's focus on this idea of as our primary example for traveling waves. Let's focus on this idea of a fixed string that is going to be disturbed, right? So what we just saw is, for instance, a triangular wave that gets set up at one point on the string, and then it travels out, right? And what we're seeing here in this demo is that each of those little dots here represents a particle or a molecule in the string, and they're talking to, or right there, there's some forces that are exchanged by the neighboring, right, by the molecular bonds of this particle to its neighbor. And so the disturbance that one particle feels, it takes some time, and eventually that propagates down the string like you see here. And now what I could do is I could also just allow me to freely move the end of this string, right? And if I move it up and down, you can see that that shape moves out, right? If I make a quick pulse, you can see that that disturbance moves down the string here. And now what I'm going to do is I'm going to vary the end of this string in a regular way. I'm going to move it up and down at some regular frequency. And when you do that, you can see that I get this kind of sinusoidal pattern, right? If I move this object up and down in a regular way, that I can send sinusoidal waves out across this rope, right? And what is the condition I need to have is that I'm moving this guy up and down at a regular rate with a fixed period, and I can generate those, right? That sinusoidal wave that moves out here. I can play with a few other features here. I can change some properties about the material the wave is traveling through. So for instance, if I have a string, I could imagine lowering the tension that I'm doing with this slider down here. And if I have a lower slider, if I lower the tension on the string and I go into my lab, what I'll find is that that pulse, that traveling wave moves more slowly through the medium, right? If I turn the tension back up again, here it goes, it's moving out more rapidly. And if I have a very low tension, then the pulse travels very slowly through the material. This is a common feature, that the speed at which a traveling wave makes its way through the material depends on some properties of the material. In this case, it depends on the tension of the string. If I have, air, it depends on the initial pressure and the density of the air. If I have fixed materials, it can depend on the density of the materials, etc. But usually the speed is fixed by some physical properties of the medium, right? For instance, we know that sound waves like to travel at the speed of sound through air because they're traveling through the same material, and the speed at which a traveling wave propagates through a material is usually fixed by the properties of that material. We can define a few other properties of a traveling wave. If I have this sort of sinusoidal behavior where I move this thing up and down, okay, now I have the tension turned down low, so these traveling waves are moving slowly through the string. We can define an amplitude for this, an amplitude for this oscillating wave, and that tells me the maximum displacement that my pulses, my traveling wave here is making away from that equilibrium position, right? If I find the maximum height that these displacements are reaching above my equilibrium position, well, that's what I call the amplitude of my wave system, right? So here you can see the amplitude is up here. That's the y displacement away from my fixed length on the string. I can also define the wavelength of this sinusoidal wave that I create by moving my wrench up and down periodically. Okay, and I can see that the wavelength is going to be the distance between these crests, right? The maximum positions for this oscillating wave are also the distance between these troughs, these lowest points. Okay, so there's some characteristic distance between those high points and low points, and that's maintained as this traveling wave moves through the material. Oh, let me get that going again. Okay, something like this. I can also talk about the frequency of the oscillation. Okay, so what I want you to do is focus on these green points along this string. And notice that the green points on the string, right, that's some fixed piece of this rope, they're going to move up and down as that wave comes through. But they don't actually themselves travel down the string, right? The string is staying fixed. There's not actually pieces of mass that are traveling down the string. The thing that's propagating is just this displacement of the rope down the string. So the fixed mass on the string, this piece of string is staying in a fixed location. And what is it going to do? It's just going to bob up and down. So this time when I do it, I want you to watch one of the green points and notice that it's just going to bob up and down. And the frequency that it bobs up and down with eventually matches the frequency. You can see that it sort of mimics what I'm doing with my wrench at the far left side. And so for any one of these points bobbing up and down, I could time how long it takes that piece of string to get to its extreme maximum and then to its extreme minimum and then back again. And I could define a period or a frequency that piece of rope vibrates up and down with. And now the last thing I want to show you with this demonstration is two of those properties we talked about, the wavelength, right? How long is that distance between the neighboring crests or neighboring troughs is related to the velocity of the rope and to the frequency that one of those pieces of ropes bobs up and down with. Now for this string with a fixed tension, what we're assuming is that the speed that, right, if I imagine that I send a pulse out, a little pulse or a big pulse, you can see that none of those pulses are catching up with the other pulses I send them out. They have a fixed velocity in this given medium. And so any wave pulse that I send out on this string has the same velocity that it travels through down the string with. So the velocity of the wave traveling down the string is fixed. But I want you to notice something about the relationship between the wavelength and the oscillation frequency. So here's what I'm going to do. I'm going to move my wrench very rapidly. That's giving my wave a high frequency. You can see those green points are moving up and down very rapidly. And you can see that the distance between neighboring crest points, neighboring high points on the string and neighboring low points is very small, right? If I have a very fast frequency, that there's not much distance between the mins and max on the string. Now look what happens if I have a medium frequency. Now that wavelength is increasing. The speed at which the pieces on the rope bob up and down is decreased, but that wave is increased, and also the wavelength is increasing here. So as the frequency decreases, the wavelength is increasing. And look, as I go very slowly, then the wavelength is getting very long, and you can see the frequency of the pieces of the rope, the time that it takes for them to go up and down is very large, and so that frequency is getting very low. So there's a relationship for a wave traveling through a medium at a fixed velocity. There's a relationship between that velocity, the wavelength of the wave, and also the frequency that the individual pieces of mass on the string oscillate up and down with. Okay. So let's jump back to the slides and write down in a little bit more detail what those relationships are. So if I focus on a sinusoidal wave, we can see now what we need, right? We have to have a source, something that's varying that medium, like that wrench, or like I'm holding the string and bobbing it up and down in a fixed way. And if I do that, I can have these regular sinusoidal waves that travel out through my medium. If I have a nice sinusoidal wave traveling out through my medium, then I can write a function to describe the displacement of the medium. Okay, we're going to call it d as a function of x and t. Now notice that this function depends on where along the string or where in the medium I am, right? Depending on which piece of the rope I pick, I'm gonna have a different behavior, right? If I went back to my demo, sometimes some pieces of the rope are down while other pieces are up, and some are at 0. And so it depends where along the rope I am. And then if I wait a little bit longer, that relationship has changed as the wave propagates through the material. So this function depends both on my position and the time. And I can write down in general this function here, okay? To describe this oscillation, I need an amplitude that tells me how large that variation, right? The maximum height that the wave reaches, and the minimum height above the equilibrium position. Okay, so I can see this amplitude A on this graph. And say in this case, this wave is traveling with some velocity V to the right here, and this is position X. I can find the wavelength of this wave by looking at the distance between two neighboring crests. And what I'm going to do is define something that I call the wave number of the wave. It's just 2 pi over that wavelength. And I have that in this function here. The wave number multiplies the position to give me something like radians, right? Remember, a sine function has to act on an angle. So this converts that distance into some angular units that I can use to then act the sine function on. I can also relate this to the angular frequency. If I look at any fixed position here, it's going to oscillate up and down with some time period t. And so then I could define the angular frequency by taking 2 pi times the frequency, or 2 pi divided by that time period t. I'm going to multiply that term, that angular frequency, times my time term in this sine function to get the time dependence here. And then all of that can have a phase offset telling me, whether or not my wave started at a maximum or a minimum at my 0 position at my initial time, This is something about the initial conditions. And we're going to practice with this as we go along here. So we have a functional form that we can use to describe how this, to describe this wave and how it travels in time. Okay. Notice here that this minus sign, as time increases, that is going to take away from my angle here. And so it's going to tell me, if I change this sign from positive to negative, it tells me whether or not I'm running positively or negatively around the unit circle. You can think about that. My angle is either increasing or decreasing. And so then it tells me, the direction that my wave is traveling in the medium, whether or not my wave is traveling to the left or to the right, depends on that sign that I have on the time dependence here. There's also a relationship between this wavelength variable and frequency variable that we defined. This wavelength has units like meters. It's a distance that wave is set up across this across this medium. It has units like meter. Frequency has units like inverse seconds, and you can see that wavelength times a frequency then has units like meters per second. It gives me a velocity, and it turns out that is the velocity of the traveling wave through the medium. And you can see then that if I had a fixed velocity like I did on the string, then I get this behavior that we demonstrated, that if I have a large wavelength, I have to have a small frequency to maintain that fixed velocity. And there's a relationship here. Okay. Some people are saying that demo looked very blurry. Do people want me to try it again with higher resolution? I'm not sure I'm going to be able to make it look better than that. Maybe if it looked blurry for you in on your live session, I might suggest, yeah, it could be people's internet depending on how it's coming through. I would suggest maybe you go back and check out that demo on the recording later this afternoon, and I think it'll look clearer there. Okay. All right. Your book also defines that velocity, right? I told you for a string, it depends on the tension, also depends on the linear mass density of the string. So if I have a heavier string, the rope will move at a fixed tension, the wave moving down the string will move more slowly. If I have sound, that sound wave depends on some physical constants that relate to the air that the object is moving through. If I have light, there are some physical properties that fix this. I'm not going to go through all, your book goes through the details of all these things. The main takeaway here is for any medium that a wave moves through, it generally moves at a constant speed through that medium, and the speed that it moves through depends on some physical properties of the medium and not the displacement of the medium that's generating the waves. Okay. And the last bit here that I want to introduce is the way that we're going to try to analyze these different wave systems. We're going to use that. We're going to do that using two different tools. One of them is called a snapshot graph. What is a snapshot graph? It's taking a picture of the displacement or indicating the displacement of a medium as a function of time t at some given time, right? At some time t. So this is like taking a picture. You could imagine the string has this wave traveling through it. If I took a picture at some instance in time of the wave, it would have some displacement of that traveling wave set up, and then that wave would move off to the right. I can also make what we call a history graph here. A history graph happens at some position X. So this is now focusing at a specific position on the rope and measuring the displacement or the change in that point on the medium away from its equilibrium position as time advances. So I can draw these two different things. I can focus at a fixed position on the rope, and I can see that that rope is going to vary in a certain way as time goes on. I can also focus at how the rope, right, all positions in the medium look like, how they're displaced away from their equilibrium position at a fixed instance in time. Okay. So let's try to work through some problems here and see if we can get the hang of working with these different relationships that we have here. Let's start with this simple problem. Let's imagine that I have two wave pulses that are traveling along the same stretched string, okay, one after another. What's true about their speeds? Well, we just saw that the equation says that the velocity on a string for some material is equal to something like the square root of the tension divided by the linear mass density. This thing is the mass of the string divided by the length of the string. So what is the answer here? Okay, let's go ahead and end this poll. Most popular answer here was C. That's absolutely correct. The waves have the same speed, right? This says that the two wave pulses are traveling along the same stretched string. So these two strings have the same tension. They're the same string, and they also have the same linear density. So that means the velocity that's related to the ratio of those two things has to be the same, and each of these are traveling with the same velocity down the string. Okay, so if I have a fixed medium, that displacement, that pulse travels at the same rate through that medium. It doesn't depend on, right, the amplitude. It just depends on the physical properties of the medium. What about this one? If I have a wave pulse on a string and I want it to travel twice as fast. What do I have to do to the tension in the string? Velocity on the string is equal to the square root of the tension over the linear density. How do I get the pulse to travel twice as fast through the string? Okay, I'm going to go ahead and end this poll. Almost everybody is selecting A here, that I have to increase by a factor of 4, right? If I want this guy to go up, I've got to increase the tension. It's under a square root. So if I increase tension by a factor of 4, my wave travels twice as fast down the string, right? So the tighter the string, the faster the rope, the faster the pulse travels down the rope. So let's imagine I have a problem like this, that I have a block that's hanging from the ceiling and it's 5 kilograms. And there's a 2-meter long length of rope that it's hanging from, or a metal wire. And I know the mass of this wire is equal to 4 grams. And then the wire is plucked at the very bottom. So I'm going to give a little wave pulse on this thing and it's going to run down the length of the string. Okay. How long does it take for that pulse to make it down this full 2-meter length? Well, let's see. The wave is traveling with a velocity here, so I know that it has some distance d, and I know that it's going to travel that 2 meters if I know the velocity of that, and I know that time t. Right? The distance that the wavelength that the wave travels is just its velocity times the amount of time that is elapsed. So if I want that time t, it's just going to be that total length, that 2 meters of wire that it has to travel divided by the velocity of the wire. So I need this velocity. How do I get that? Well, this is a metal wire or a string, so I know that that velocity of the wire has got to be like square root of the tension in the wire divided by the linear mass density. The linear mass density is just defined as the mass of the wire divided by the length of the wire. I know these terms. They told me that this is a 4 times 10 to the minus 3 kilogram block. Sorry, the wire has a mass of 4 times 10 to the minus 3 kilograms, and that the length of the wire is 2 meters. How do I find the tension in the wire? Well, this block here, this 5 kilogram block, is dangling and it's not changing position. So I know that this block is in equilibrium here. I know that there's mg pulling down, and then that tension is pulling up and counteracting it. So I know the tension in the wire has to equal the mass of the block times mg, and that's a 5 kilogram block times that gravitational acceleration constant. I know this tension now. I know this linear density. I can plug those into this equation to find the velocity that the string takes. Once I have that velocity, I can plug it into my equation here and find the time that it takes for the string to reach that upper end, or for the pulse on the string to reach the top of the ceiling. Okay, let's talk a little bit about how to interpret and move between these snapshot graphs and history graphs. So in this figure, what I have is a snapshot graph that's made at time t0. So I imagine that you could think about this like a string, and there's some displacement in the string, and it's got this funny looking triangular pulse that's moving down the string. And I take a picture of it at some instance, and I call that instance t0, or time 0. And I know that in this particular string, because of the density of the string and the tension that's set up in it, that a pulse is going to travel at 1 meter per second through the medium. What is the snapshot graph going to look like 4 seconds later? What is that going to look like? Well, let's see. This wave is going to be propagating down this string and moving to the right at 1 meter per second. So in 4 seconds, each piece of the string, each kind of displacement feature that I see on the string is going to have traveled 4 meters to the right. So this maximum raised point is going to be 1, 2, 3, 4 meters displaced here. And this sort of midpoint where it's at 1 meters is also going to be 4 meters displaced. And this low point is also going to be moved to the right at 4 meters. And so that pulse will be moved by 4 meters after 4 seconds. And then it'll still be continuing to the right at its 1 meter per second. What about this? What does the snapshot graph look like at -2 seconds? Okay. -2 seconds happened earlier in time. That was basically like, where was this pulse 2 seconds before I took that initial picture? So I know 2 seconds before I took that initial picture, that pulse had to be 2 meters further to the left. So this maximum point is back 2 meters at this point. This point where it's raised up 1 meter is also back by 2 meters. And so I would have that triangular pulse is shifted back by 2 meters when I was at time -2 seconds. So if I know the speed in the wave and the direction that it's traveling, I can draw different snapshot graphs, where that wave pulse, how that wave looked as the wave propagated through this medium. What about the history graphs? Can we make a history graph as a function of time? Let's see if we can do that together. So what is a history graph? A history graph is a function of a function of time. And I'm going to look at the displacement d for some fixed position. Right now it says to start, I want to look at x equals 0 meters. Well, what does the history graph for x equals 0 meters look like? Where is it? I can look on the snapshot graph and see that x equals 0 meters is right here. So at time 0, I can add that I know that there's no displacement. And now as time goes forward, as I move time forward, that pulse is moving to the right. And so that position, if I'm just looking at this fixed position, I'm just looking at this fixed position, as that pulse moves to the right, as time increases, I'm never going to get an increase in the displacement. That string at position 0 is just going to stay fixed. Now, if I look backwards in time, I can see that at time 2 seconds, that, if I say -1 second, -2 seconds, that green pulse that I see in that upper plot, that was the pulse for what this medium looked like at time -2 seconds. And I can see that position 0, where I have that arrow pointing, had a maximum displacement, went up to its maximum displacement of 2 at that particular instance in time. What's the displacement d in the string at -1 second? Can you guys tell me that? What would the displacement in the string be at position x equals 0 meters at time -1 second? Anybody have an idea? Well, let's look at the snapshot graph. This is the pulse at -2 seconds. 1 second later, this pulse is going to shift to the right by 1 meter. So that's the pulse at t equals -1 second. What's the displacement there at this position in the rope? I can see that at that time -1 second, well, now the rope is at right, this 1 meter. And then if I wait again to 0, this thing has to fall away like this. So the history curve looks like this. The wave is moving, right? You can think about what this is telling us. The wave is coming from the right. At time -2 seconds, that's when the wave hits position 0, and I get this maximum displacement, the first instance in time that wave pulse hits position x equals 0. And then as that wave pulse makes its way through position x equals 0, the displacement in the medium drops down, and then as that wave pulse moves away from that position, the medium maintains this 0 displacement and becomes flat. Let's try that again at a different position. So let's focus at position 4 meters. X equals 4 meters. What's the snapshot graph? Sorry, what's the history graph going to look like at position 4 meters? What would I change on my graph that I have drawn here to indicate what happens at position 4 meters? What do we have to do? Well, look, everything that happens at position 4 meters, yeah, you would have to shift it by a term, right? Look, this wave is propagating through the string. So everything that happened at position 0 meters is going to happen at position 4 meters, but sometime later. How much later? How long does it take the pulse to make it from, say, its initial position to that position at 4 meters, at 4 meters? How long does it take for the pulse to go from 0 meters to 4 meters? How long does it take to go from 0 meters to 4 meters, right? That's the distance that we're looking at on these history graphs. There's a 4 meter difference between those 2 points we're observing. How long does it take for the wave to propagate 4 meters in this example? It takes 4 seconds, right? We know the speed is 1 meter per second, so it takes 4 meters for that wave to, or 4 seconds for that pulse to travel from 0 meters to 4 meters. That means everything that happens to the string at position 0 happens to the string at position 4 meters just 4 seconds later. So if I just add 4 seconds to all of these time bits here, right, then I would get that this is at 2 seconds, and this is at 3 seconds, and this happens here at 4 seconds. You can see I get that same behavior here, right? You can see that by the time, right, we drew this wave pulse at time 4 seconds, well, it's already passed through this 4 meter position, so it's back to 0. When was this wave at this position where it was reaching its maximum? Well, that was 2 seconds early when I was at 2 seconds, and it reaches this kind of in between position when it's at 3 seconds. So the same thing happens. The wave first hits position 4 meters 2 seconds after that original picture that we looked at, and then it decays away to 0 at time 4 seconds. So because the wave is just traveling through the medium, these history graphs will look the same for all positions on the string, just shifted in time, right? Just shifted around in time. All right, what about this one? This figure shows a history graph. Now I'm showing the time at some fixed position, x equals 0. Can we draw the history graph at position 1 meter? So this is a wave traveling to the left at 1 meter per second, right? At 1 meter per second. So let's just draw a sketch of the wave, right? So I have a wave pulse. Let's just guess what it might look like, or it's probably down like this, and it's traveling to the left at 1 meter per second. So this is at, right, this history graph was at x equals 0. And now I want to draw a snapshot graph, or sorry, a history graph for x equals 1 meter. What do I have to change about this history graph? How does the time shift at position x equals 1 meter? You shift everything to the right by 1 second. Everything is going to happen earlier. This wave is moving to the left. So everything that happens at position 1 meter is also going to happen at position 0 just 1 second earlier. So I can draw that. This thing is shifted back by a second here. So I know that that snapshot graph, or sorry, the history graph for d x equals 1 t should look like this red curve. Let's try to draw now the snapshot graph at time equals 1 second. The snapshot graph at time equals 1 second. Oops. Let me go ahead and erase this and make a more careful diagram. So the snapshot graph is going to show the displacement as a function of position x along the medium. And I want to do this at t equals 0. I'm sorry, t equals 1 second. Okay. What is this going to look like here? Well, let's see. I can look at my history curve at t equals 1 second. So here's t equals 1 second. And look, this says at 1 second, right? At 1 second and position 0, that my displacement should be 0, right? I'm looking at the black curve, that's position 0. And if I read it off at position at time 0, I'm at this point here. Or sorry, at time 1 second, I'm at 0. But now if I move to 1 meter, what's the displacement? Well, I can see at 1 meter that I'm at -1 on the red. I'm reading that off of the red curve. What's my displacement going to be at position 2 meters? At time 1 second. Well, what is the snapshot graph? What does the history graph look like? At position 2 meters, because this thing was moving to the left, right? That wave would have been, again, everything would be happening 1 second earlier. So this would be d equals x of 2 meters as a function of time. And look, now I can read off from this. At that time, at t equals 1 second, the displacement at position 2 meters is going to be -1. Or sorry, -2. I'm going to be at my maximum displacement. And then everywhere else, it's going to be 0. And so I get that I have this pulse in position that looks like this, and it's going to be moving to the left as I move through this medium. Okay. All right, we're going to stop there with today. for today. We're going to pick up with this idea tomorrow. So we'll do maybe 1 or 2 more examples of going between history and snapshot graphs. And then we're going to practice using that functional formalism for sinusoidal traveling waves. And then we'll conclude this chapter. All right, thanks everybody so much. Hope you have a good rest of your day. Again, if the video looked blurry for you, I saw a few people making those comments. Hopefully the video looks clear. Please do take a look back on the recordings that I'll post this afternoon. All right, I will talk to you all tomorrow. I hope everybody has a good day. All right, bye now.